G'day, welcome back to Mathematics for another extension to maths lesson. We're starting off with a flashback to the proof topic where we're going to look at a proof by contradiction to show that the square root of 7 is an irrational number. This is going to be a sort of quick version. If you want a longer version of proofs like this, go back to my proof by contradiction video if you are interested. Okay, here we go. We start off by assuming the opposite of what we're trying to prove. So we assume that root 7 is a rational number. Now, a rational number can be expressed as a fraction of two integers which have no common factors. So here's how we write that. So there exists two integers a and b such that root 7 is equal to a over b. A and b are co-prime, which means that a over b is already a simplified fraction. Now, we're going to try and show that this does not make sense. So the way we do that is we take both sides of the equation and we square it like this. So we get 7 equals a squared over b squared. Multiply the b squared across, so we have 7b squared is equal to a squared. Now this line here tells us that a squared must be a multiple of 7, okay? And if a square number is a multiple of a prime number, it means that the square root is also a multiple of that prime number, okay? So we're allowed to say a squared is divisible by 7. That implies that a is also divisible by 7. So we can write a as 7 times something. That something is an integer. Substituting a equals 7k into the line above gets us 7b squared equals 7k all squared, which is 49k squared. Now we take both sides and divide by 7, and we get that b squared is equal to 7k squared. This tells us that b squared and by extension b are also divisible by 7, and there is your contradiction. So we have shown that a and b can both be shown to be divisible by 7, which means a over b is not simplified, they aren't co-prime. So this doesn't make sense because our assumption was false. Root 7 is not a rational number, it is irrational. Cool stuff. On to the next one is a flashback of the harder types of induction questions we were doing in the last video involving inequalities. This one's from the 2020 HSC exam and it was worth 4 marks, so quite a lot of work to be done here. All right, starting off with our initial assumption, our base case for n equal to 2. So on the left-hand side, we have 1 over 2 squared. On the right-hand side, we have less than 2 minus 1 over 2. That works out to be a quarter, which is less than a half. So the inequality holds true when n is equal to 2. So that's our first step done. Now we're going to assume that when we choose an arbitrary integer k, that the inequality holds. And we're going to use this assumption to try and show that it works for the next integer, which is k plus 1. So we're adding one more term to the series on the left, and on the right-hand side, we're changing the top to k on k minus 1 plus 1, which is k, and on the bottom we have k plus 1. All right, so now the goal is use our assumption to prove true for n equals k plus 1. Here's how we do it. We're going to take our assumption, and we're going to add to both sides 1 over k plus 1 squared. Okay, so taking this top line up here and adding to both sides of it, 1 over k plus 1 squared. All right, now what we're going to try and do is play with the right-hand side and make it look like k over k plus 1, which is our target, or try and make it at least look bigger than k over k plus 1. So what we'll do is we'll combine these two fractions by making a pair of common denominators. So we're going to multiply the left-hand fraction, top and bottom, by k plus 1 squared, and the right-hand fraction will multiply top and bottom by k. Now we'll combine the fractions, and while we're at it, we may as well expand this k plus 1 squared to k squared plus 2k plus 1. Okay, because we're going to need to fully expand and simplify the top so we can have a look at what we're working with. So that's our next step. We're going to expand out these brackets, and when you simplify the whole thing, take my word for it, you end up with k cubed plus k squared minus 1. Okay, that right there is the top of the fraction expanded and fully simplified. Okay, now here's where it gets a bit tricky. Here's a cool way you can very quickly show that this is indeed greater than k over k plus 1. What we're going to do is actually factor out of the top of the fraction a k squared. Okay, taking out a common factor of k squared gets us inside k plus 1, and then when you divide 1 by k squared, you end up with 1 over k squared. Okay, so we're just sort of expanding this top line. Now the reason we've done this is because now we can simplify this fraction a little bit. We can divide top and bottom by k, so we can get rid of those two k's, and then we're going to take a k and a k plus 1 out the front. Okay, the reason we're doing that is because if you remember what we were trying to prove, the right-hand side was a k over k plus 1. Okay, so we simplify the k's, we take a k over k plus 1 out the front, and now we have k over k plus 1 times k plus 1 minus 1 over k squared over k plus 1. Now, the reason why this is good is because this fraction on the right here that's multiplying our target, we have k plus 1 minus something on the top, and on the bottom we have k plus 1. So what we have here is we have a fraction where the top of the fraction is clearly going to be smaller than the bottom of the fraction, because we've got the same thing, which is k plus 1, but on the top we're taking something away. So let's say the top could be 4, the bottom would be 5. Okay? What this means is that this fraction is less than 1 because the top is smaller than the bottom. Okay? This fraction is less than 1, which means that this entire expression must be less than k over k plus 1, because we're taking k over k plus 1 and we're making it smaller by multiplying by a fraction less than 1. Okay? That's how we explain why this expression is less than k plus 1. And so then we've shown that this right here, which was our left-hand side, is indeed less than k plus 1. And there is our proof by mathematical induction. Yeah, a bit of a hectic one. To get 4 marks in that, you have to be pretty switched on, in my opinion. All right, today we're looking at applying mathematical induction to solve or prove familiar formulas, what I would say it is. Just like, yeah, just a few examples of cool stuff we can do with mathematical induction that you may not have seen before. So let's just dive in. Okay, first one would be new for most viewers of this video. It's called recursive formula. It's just, it's a formula that is recursive. Yeah, exactly. So we have a formula right here. So this is the nth term of a sequence, Tn, is equal to Tn minus 1, so the term 1 before that, plus n. Okay, so right here is a formula that gets you from one term in a sequence to the next one. Okay, we know that the first term is 1, and we're trying to use mathematical induction to prove that the nth term can also be expressed as half of n times n plus 1. Okay, so this is the information that we're given, these two expressions here. We're trying to prove this formula here using mathematical induction. Okay, so as always, first place to start is with your base case, which is when n is equal to 1, because we're trying to prove that this formula works for n greater than or equal to 1. Now, when n is equal to 1, we're expecting this nth term formula to get us the first term, which the question said is 1. So let's see if that works. So the first term is equal to half times 1 plus 1. So we get half times 1 times 2. So we end up with half times 2, which is indeed 1. So we have shown that the formula gives us the first term that we were supposed to get, which is equal to 1. So it's true for n equals 1. Now we're going to assume that if we chose a generic integer k, that this formula would work for the kth term. And we're going to try and use this assumption to prove that it also works for the next term, which is k plus 1. Okay, so taking our formula, changing the k to a k plus 1, and changing the k plus 1 to a k plus 2. Okay, now here is where we get our recursive formula involved. Okay, we're using the fact that this formula right here says that a term is equal to the term before it plus the number of term that you're looking at. Okay, so we're going to take the left-hand side, which is term of k plus 1, and we're going to express this as term of 1 less, which is going to be the kth term, plus the subscript of the term we're looking at. So up here it was n, down here it's going to be k plus 1. Okay, so this right here is me using my recursive formula from the question. We have the term equal to the term before it plus the number of term that you're looking at right here. Okay, now we can use our assumption because we have an expression for the kth term right here. It's equal to a half of k times k plus 1. So let's chuck this into our expression here. So we get half of k times k plus 1 plus k plus 1. Now our goal is just to play around with this and try and make it look like the target, which is right here. So the way we can do that is we can factor a half out of everything, because we can see in our answer we need a half out the front. So taking a half out of the k plus 1 on the end leaves us with 2k plus 2. Now if we expand that out and simplify it, we end up with k squared plus 3k plus 2 inside the brackets. That very conveniently factorizes to k plus 1 and k plus 2. And right there was our target for the k plus 1th term. So there you go, the formula works because we have proved it using mathematical induction. Another example of recursive formula, because these are new, so they might take a little bit of getting used to before you start to feel confident. We have the nth term is equal to 2 times the term before it, plus 2, take away n. First term is 3, and our recursive formula, our formula that we're trying to prove is that the nth term is also equal to 2 to the power of n plus n. All right, let's dive in once again, starting with our first term when n is equal to 1. We are hoping that this formula gets us the first term of 3. So let's have a look. Initial case, we get the first term as 2 to the 1 plus 1, which is indeed 3. That's what we wanted from the question, so therefore the initial case is holding true. We are on a roll. All right, let's keep going. Assuming true for the kth term, so we're going to assume that that tk is equal to 2 to the k plus k. Let's try and use that to show that this works for the next term along, which is the k plus 1th term. Once again, we are going to try and prove this formula using the recursive formula from the question, which is that the term is equal to 2 times the term before it plus 2 take away n. So right on the left-hand side, the term of k plus 1 is 2 times the term before it, so this is the kth term, plus 2, and then take away which term you're looking at, which is k plus 1 instead of n. Okay, now we're going to use our assumption where we use that the kth term is equal to 2 to the k plus k, so we're going to substitute this into right here. So 2 times 2 to the k plus k plus the rest. Now if we expand this out, 2 times 2 to the k is going to give us 2 to the k plus 1, because we've got 2 to the 1 times 2 to the k. We've got 2k here, we've got the 2 minus the 1, we can just write as plus 1, and the minus k just chilling. Now if we fully simplify it, we end up with 2 to the k plus 1, 2k minus k is just k, and then you've got a plus 1, and if we look at our target, that's what we were trying to find. So we have shown that it is true through the magic of mathematical induction. So we throw up a QED, throw our fists in the air, and go on to the next question. Lovely. All right, up next, we are going to prove that the famous interior angle sum of a polygon formula is indeed true because it works through mathematical induction. So in year 9 or 10, you were probably taught that if you take the number of sides of a polygon, you take away 2 and then multiply by 180, that's going to give you the total angle sum of the inside of the polygon. So for example, for a pentagon, you would do 3 times 180. We're going to show that this works using mathematical induction and a bit of proof by diagram. Let's start off with our initial case. For this question, we need to assume that a triangle has an angle sum of 180, which it does, which is good to know, but otherwise this doesn't really work. We need initial starting point, so we have an assumption to make, which is that, yeah, triangle has 180 degrees. So the smallest possible polygon is 3 sides, because you can't have a 2-sided polygon because polygons have straight sides, but anyway. So for our triangle, 3 minus 2 times 180 is indeed 1 times 180. So this is true. We know the angle sum of a triangle, so the initial case is working. All right, beautiful. Now we're going to assume that if we had a k-sided polygon, the angle sum would be k minus 2 times 180. Okay, right here is my k-sided polygon. It looks like a 5-sided polygon, but it's actually not. It's got k sides, so that's really embarrassing for you. All right, we're going to use this diagram to add on an extra side and then show that the assumption can help us prove true for k plus 1. So if we want to add a side to this polygon, what we would need to do is take away one side and then add 2. Okay, we can't just add on an extra side because it wouldn't have anywhere to go. So to add on one side to our polygon, we take away one of the edges and we replace it with 2 more, like this. Okay, that right there is me taking away that side there between A and B and adding in from C from A and B. You know what I mean? Okay, so this right here is our k plus 1 sided polygon, and we're going to try and show that this has an angle sum of k plus 1 take away 2 times 180. So what we've essentially done here is we have taken away one side, added 2, which means we've taken our polygon and we've added into it an extra triangle. Okay, so if we take the angle sum of our k-sided polygon, add on our triangle, which we assumed in the question is 180 degrees, then we can try and make it look like this. So let's have a go. So we've got our angle sum, we've got our k-sided polygon right here from our assumption, adding on our triangle of 180. And now if I was smart, I would have just factorized this, but I'm not smart, so I decided to expand it. So expanding this out, we get 180k take away 360 plus 180. Then we get 180k take away 180 degrees. We factorize this to k minus 1 times 180 degrees, and then we write this minus 1 as a plus 1 minus 2, because remember, this is what we're trying to show. Okay, so writing minus 1 as plus 1 take away 2, we have indeed shown that the angle sum of the k plus 1 sided polygon is k plus 1 minus 2 times 180. Proof by diagram, QED, we did it, success. Moving on with my life. All right, bit of calculus. All right, you've used the product rule, or sorry, you've differentiated a lot in your life, but I bet you've never proved the differentiation actually works using mathematical induction. So let's do that. We're starting off with the first principles definition of a derivative to show that the derivative of x is equal to 1. That's going to be our initial case that we can use to show that the derivative equation right here actually works. All right, so let's dive in. Let's start off with our first principles differentiation, which you may be a bit rusty on because it's not really covered a lot in year 12, but hopefully you saw this in year 11 at some stage. This guy right here, the derivative is the limit as h approaches 0 of the function of x plus h. Take away the function over h. So our function is just x. So for the top, we're going to have x plus h, and then we're going to take away x divided by h. Okay, as long as you've got the right formula, everything works out pretty simply because the x take away x cancels out. So we end up with h over h, which is of course 1. And so then we just have the limit as h approaches 0 of 1, which is indeed 1. So there you go. By the definition of the derivative of x is equal to 1. Sweet as. Now let's use that to prove that the derivative of x to the power of n is equal to nx to the n minus 1. Okay, we're going to start off with our initial case, which is when n is equal to 1. So we know from part A that when n is equal to 1, the derivative should be equal to 1. So let's see if our formula gets us that answer. Okay, derivative of x to the 1 is equal to 1 times x to the 1 minus 1. So we get 1 times x to the 0. X to the 0 is of course 1. And so this is true because we had the derivative being 1 from part A. So there is us proving it's true for the initial case. Let's now assume that when n is equal to k, the derivative of x to the k is equal to kx to the k minus 1. Let's try and use that to show that the derivative of x to the k plus 1 is k plus 1 x to the k. Now, the question said we are allowed to use the product rule here because we're going to start with the left-hand side, the derivative of x to the k plus 1. We're going to think of this as x to the k times x to the 1. Okay, so writing the left-hand side as x to the k times x to the 1. Now we're going to differentiate this using the product rule because the question specified that we were allowed to do that. So for our product rule, if we differentiate the x to the k from our assumption, we get kx to the k minus 1. We leave x to the 1 all alone. Then we add to that, we leave the x to the k alone, and we differentiate the x to the 1 to a 1 from our part A. Okay, there's us applying the product rule. Now we're going to simplify it as best we can. So we have x to the k minus 1 times x to the 1. This turns out to be x to the k if we simplify our powers. So we have k x to the k. Then on the end, we have x to the k times 1, which is x to the k. We have an expression we can factorize. We have a common factor of x to the k. If we factor that out, we get x to the k times k plus 1. And what do you know? That was our indeed intended target. So we have answered the question using our assumption, QED, it works. Okay. All right, anything more to say about that? Absolutely not. On to the next question. Okay, moving on from calculus now and looking at some complex numbers. Our very familiar formula right here is called de Moivre's theorem, and we are going to prove that this is true using mathematical induction. Okay, let's kick off with our initial case of n equal to 1. So z to the power of 1, we want to show that this is equal to r to the 1 times cos 1 theta sine n theta. Luckily on the right hand side, r to the 1 is just r, and then we have just cos theta and I sine theta. And z to the 1 is just z, and so this is clearly a complex number with modulus r and argument theta. So this must be true, therefore the initial case is holding true for n equals 1. Very exciting, I always love the first step. Almost as exciting as the second step where we rewrite the exact same thing with a different letter. This is fun, let's go. The assumption for n equal to k, we are going to assume that de Moivre's theorem holds true for k. This is going to be our ammunition to prove that it's true for the next term along, which is k plus 1. Okay, so what we're going to do here is writing the left-hand side as z to the k plus 1, as we've done a few times today. We'll write this as z to the k times z to the 1. Z to the k is right here from our assumption, and z to the 1 is right here from part A. Now, we are going to multiply these together using a bit of a tricky binomial expansion. So out the front, we'll have r to the k times r to the 1, which is r to the k plus 1. And now inside we have a bit of a mess, but it's going to tidy up really nicely. We've got cos k theta cos theta cos k theta I sine theta. We've got I sine k theta cos theta in the middle, and then on the end we have I squared sine k theta sine theta. All right, lovely. Now, the trick here is to write the inside of your bracket or your trigonometry mess. We're going to write this in a really clever way, like this. Okay, we have cos k theta, cos theta at the front. The I squared on the end turns into a -1, so we're writing the real parts at the front all together. So sine k theta, sine theta. We factor the imaginary constant out of the imaginary parts, and there we have sine k theta, cos theta, sine theta, cos k theta. Now, if you're watching this video, I'm assuming you are an Extension 2 student, which means you are an expert of Extension 1 mathematics. And that means you recognize this right here as a trigonometric identity. This is in fact cos of k theta plus theta. Okay, this is the sum of cos theta. So if you look at your formula sheet and look at cos A plus B, it'll look something like this. And on the end here, again, if you look at your formula sheet, you'll see this is looking very similar to sine of A plus B, where A is k theta and B is theta. If that's making zero sense to you, you might want to flick back through your Extension 1 notes and just do a bit of a refresher, because all of that is assumed knowledge for Extension 2. Okay, but those who are with me can recognize that we can write the front half as cos of k theta plus theta using our angle sum formula. And inside our imaginary part, we can write this as sine of k theta plus theta. All right, this is really good because inside our angles, we can factor out a common factor of theta, and we end up with k plus 1 theta and k plus 1 theta. And that's what we were trying to prove. So we've got a modulus of r to the k plus 1. We have an argument of k plus 1 theta. Using our assumption, it works for k plus 1, so we have proved the question QED. Lovely. Okay, onto our penultimate question. This comes from a NESA sample exam from 2020. It's a bit of an interesting one. We've got cubes being stacked in the corner of a wall that go either up against the wall or along the other two walls. Okay, making a solid shape. The one here has 9 cubes. Cool. Let n be the number of cubes used to make a solid shape in this way. Use mathematical induction to show that the number of exposed faces of the cubes in this image is 2n plus 1. Okay, we're trying to prove that n cubes will have 2n plus 1 exposed faces. Okay, let's start with our base case of 1 cube. So when we have 1 cube, here's my corner. I'm just going to chuck a cube up there. All right, 1 cube. How many exposed faces? 1, 2, 3. Let's see if that works with our formula. What do you know? 2 times 1 plus 1 is indeed 3. So 1 cube, 3 exposed faces. That works with the formula given to us from the question. And my neighbors are doing a bit of yard care. I'm just going to go shut the window. Be right back. All right, I'm sure I'll make a mental note to edit that out. All right, so it works for the first case. Let's now look at k number of cubes. So we're going to assume that a generic number of cubes will have 2 times k plus 1 exposed faces. Let's just say in this picture here, I know it looks like 9, but it's actually going to be k cubes. Now we're going to look at k plus 1 cubes. So we're going to add an extra cube to the diagram given to us from the question. So there's 3 ways we could do that. We could chuck a cube here, we could put a cube here, or we could put a cube here. This is some really high level PowerPoint skills here, guys. All right, it doesn't matter where we put it, whether it's here or here. What we're doing is we're taking away one of the exposed faces because we're covering it up. Okay, we're taking away one face, but we're adding on another 3. Okay, so we're taking one away, adding on 3. So k plus 1 cubes, we have the number of exposed faces of the k cubes. Like I said, we're covering one up and then we're adding on another 3. So we end up with, if we expand and simplify this, we end up with 2k plus 3. We're trying to show that it's equal to 2 times k plus 1, which we can do. We can write this as 2k plus 2 plus 1, factor the 2's out of the front 2 terms, and then we have 2 times k plus 1 plus 1. Therefore, using our assumption, the formula holds true, and therefore it must be true for all k, or for all n, by mathematical induction. So there you go. Next time you're stacking cubes in a corner, I hope you think of this question and think about mathematical induction. All right, on to our final question we're going to prove that it is possible to cover a 2 to the n times 2 to the n grid with L-shaped tiles consisting of 3 squares if one square of the chessboard is removed? It's not a really well worded question, but so it's a chessboard, which is like a grid of black and white tiles. We're going to show that as long as the length and width of your chessboard is 2 to the power of something, you can always cover that chessboard with a 3 square L shape like this. Okay. Right here is our initial case. We've got a 2 to the 1 by 2 to the 1 chessboard. We've removed one of the squares, and then what we can do with the rest is cover it with a 3 tile L shape. Okay, so there is our 2 to the 1 chessboard. It works. First case done. Okay, here is our 2 to the k times 2 to the k chessboard. Okay, I don't know what it is, but I'm going to assume that I can take away one square and then fill the rest with these L-shaped tiles. We're now going to use this chessboard to show that it works when we have a 2 to the k plus 1 times 2 to the k plus 1 chessboard. Here's what that chessboard looks like right here. Okay, because we're taking our sides and we're going from 2 to the k to 2 to the k plus 1, we're taking our length and our width and we're doubling them. Okay, if you go from 2 to the k to the k plus 1, you are doubling. So we're really going from one of these chessboards to 4 of these chessboards. Now that's convenient because we can put our 4 chessboards in a way so that those missing squares all meet in the middle, and then what's in the middle is a 2 to the 1 by 2 to the 1 chessboard, which we already looked at from the initial part of the question. This can be covered by one L-shaped tile, and then we have one square remaining, and there is your question done. Okay, so we're taking our 2 to the k times 2 to the k chessboard, multiplying the length and width by 2. We have 4 missing squares in the middle. We cover 3 of them with an L-shaped tile, and then you've got one square removed, and that's what the question was asking us to prove. It's pretty weird, but I think it's cool. One of my students showed me this a couple of years ago, and he explained it in a much better way. So, Shanglin, if you find your video, please post it and do a better job than this. Thank you, sir. All right, that'll probably do it for me today. Hope you watched and learned something. Or actually, I just hope you're having a good school holidays, because that's what I wish I was doing. All right, here's some recommended exercises for my students if they are watching this, and everyone else, I'll catch you in the next video. We'll be starting integration, which is my favorite thing in the entire world, so I'm really looking forward to it. All right, happy holidays. Look after yourselves. Adios for now.